I am a protector, exploring the expanses of space to keep our planet safe, and all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel, and a sea of people to find a lost child. I'm a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. Make us whole again. I am a visionary, enabling taxis that don't need steering wheels, and those that don't need roads. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Imagine that. Every single score for every single instrument in an entire symphony orchestra being composed by an AI. So if a machine can do that, imagine what we can do to companies. So that's what I'm going to talk about. Good morning, everybody. I'm Shanker Trivedi. I head up the enterprise businesses at NVIDIA. I started NVIDIA 10 years ago. Our enterprise business was $0 million. And we're now about $1 billion a quarter. I still have the same job. And I love my job. And today, I'm going to share with you my perspective on AI and how it's changing industries and the customers that I work with. And I'm going to focus today more on machine learning than on deep learning and supercomputing. So here you have it. You open the newspaper, you look at your Google alerts, you look at your favorite blog site. Everywhere, AI is transforming industries. 4 out of 5 movie recommendations on your Netflix stream are delivered by a recommender powered by AI. Apparently one third of Amazon's shopping is powered by the recommendation engine. The 1/3 of the items people are buying are not what they went to buy. It's kind of like, my family and I go to Costco and we go to buy one thing and we end up with 15 different things. I think e-tail shopping is exactly that, powered by AI, essentially adding 40% to retail revenues just because of technology. And as I sort of reflect on this, the key thing for me is every one of these companies is becoming or is already a computing company. So think about it, for sure, Uber is a computing company. Now, if you think about Tesla Motors, which is doing electric self-driving cars. I think it's much more of a computing company than a car company. Car companies used to make internal combustion engines, with petrol and diesel, and now there's just a battery. And so the car company is becoming a computing company. And I could go on, a medical imaging company is a computing company. A logistics company is a computing company. And all of these computing companies are powered, so to speak, by data and by computers. And the people who drive and own and transform these companies are computational scientists and data scientists, people like you in this room. So think about it. That's your job, to transform your company into a computing company. And so that's kind of my perspective on this. So let's talk about why this transformation has happened. These algorithms and methods have been around for many years. But what's happening is, and people started to build out these CPU server farms to run all sorts of computing. People started to invest in lots and lots of storage to process and manage all the data. But here's what's happening. The computing requirements are growing exponentially. The data requirements are growing exponentially. There's a graph on the right, and you can see sort of, Moore's law used to be 10x every 5 years. 10x every 5 years, which means 100x every 10 years. 1,000x every 15 years. And it used to be like that when I was a boy, and we took advantage of CPU computing. But now, Moore's law has run out of gas. And so we need a new type of computing, and we call it GPU-accelerated computing. A new type of computing that can deliver that 1,000x every 15 years. 1,000x. And so lots and lots of people embrace GPU computing. We've got 1 million developers now, about 8 million downloads. People are just embracing it. Why? Not just because it's cool, but because you need it in order to drive the requirements of the future. And so thank you all for joining our developer program. Now everyone thinks about GPUs as like the chip, And the chip is very powerful. It's got lots and lots, 5,000 cores in our latest V100 processor, hugely fast memory and so on. But GPU computing is more than just the processor. So here on this chart, I've shown you the platform. And the platform is built on something called CUDA, Compute Unified Device Architecture. And on that CUDA platform, we get tons and tons of software. Software written by NVIDIA and software written by our partners, such as H2O and IBM and others. And if you look at that layer in the middle, which starts with Clara, these are the vertical stacks of software for different industries. So Clara is our stack for healthcare. It allows you to GPUify, to accelerate all the medical instruments, imaging and pathology instruments out there, and add AI to them so that we can take advantage of the huge amounts of data that these machines are spewing out. NVIDIA AI is our stack for artificial intelligence deep learning, starting with CUDA and all the accelerated frameworks and the inferencing server and so on. Rapids I'll talk about a little bit more in a moment. Isaac is our robotic simulator. You can train thousands and thousands of robots to do the same thing instead of manually training them. Drive is our self-driving car platform used by lots and lots of people, and Metropolis is what we use for video analytics. So think about GPU-accelerated computing, not just the chip, but a platform for developers to develop solutions for vertical markets and industries. And we package up these solutions, these stacks, into something we call the NVIDIA GPU Cloud. And the NVIDIA GPU Cloud is not a cloud service. It's a repository of applications that are performance-tuned and optimized to run on single GPUs, single nodes with multiple GPUs, and scaling out using Kubernetes on multi-node sort of server farms. So that's our value proposition for you, our developers. So let's switch gears and now talk about data scientists. And so you're looking at this huge amount of data, you're trying to figure out what to do with it, and basically it just takes a lot of time. 30 hours just to build a gradient boost decision tree, hours and hours. And here's the thing, the models are getting more and more complicated. And increasingly, we're putting together ensembles of different models. A bit of this, a bit of the deep learning, a bit of machine learning, a bit of gradient boost, some amount of k-means, etc. Models are getting more and more complicated. It's taking a lot of time for all of the relatively few people that we have out there who are able to do this. So part of it is we want to get out there and evangelize and help all of you become more productive. And then the other part of it is how do we democratize it so that everybody, normal people with a normal IQ, can do machine learning and deep learning. So that's kind of where we are coming from. And so what we did was we said, okay, we've done a pretty good job on deep learning. We've put together all these containers with accelerated frameworks. We've put together an inferencing server. What could we do with traditional machine learning? What could we do? So the first thing which we said is we've got to speed up key algorithms. So we looked at gradient boost, and working with our friends at H2O, we found ways to speed up gradient boost more than 50 times compared to a single CPU server. We've now looked at k-nearest neighbor, which is either statistical or maybe you can solve it using graph analytics, and again, speed it up around about 80 times for k-nearest neighbor. We're looking at Kalman filters, we're looking at k-means clustering, and so on. So that box that you see in the middle called model training, we're focusing on speeding up the execution times as much as possible. But what we found was when we looked at the wall clock time, end to end, from the time you start a job to the time you finished a job, we found a lot of time was being used up in data preparation. And so you ingest all this data, and then you need to prepare it in a way that is suitable for machine learning. And the good news is we've now found a way to speed that up. And we call that CUDF, CUDA data frames. And with doing both of these, we can see wall clock speed up times, which are amazing for each of you. And of course, by the way, once you do all this model training and you sort of start to figure out what the insights are, nobody does visualization better than GPU computing. So let me show you the before and after. So this is what Rapids is doing. It's addressing data preparation, model training, and visualization. And on your left, you can see before Rapids, you had, obviously most of you are using Python, some of you still use C. You had Pandas for data array. You had INRIA, scikit-learn for all the traditional statistical and machine learning algorithms, and then NumPy, which is the data format. And Dask is what people use to parallelize Python. And so we saw this, wow, now we have an opportunity to add significant value. So by putting in the things in the green box that you see on the right, and leveraging Dask for parallelizing, and leveraging Apache Arrow, which is a multi-language parallelized in-memory data array, we basically are able to get huge amounts of acceleration for traditional machine learning. If you look at Jensen's our CEO, he did a keynote the other day in Munich at our GTC, and he took live on stage, took the entire 400 gigabyte Fannie Mae database for mortgages, and in the background there was the Pandas script flowing on a CPU only. Even if you use 100 CPUs, it takes an hour to prepare the data on this 400. Think about it, 100 CPU servers takes 1 hour to prepare 400 gigabytes of Fannie Mae data. The GPU, one single GPU, did it in less than 2 minutes, right? 1 hour to less than 2 minutes. In other words, you get much, much more productive. So basically, the blue box on your left is before GPU-accelerated machine learning. The box on your right is after GPU-accelerated machine learning. CUDF is our library for data frame. CUML is all the accelerated libraries, the work we've been doing with H2O and many others to accelerate individual algorithms for machine learning. And then on the right, we have this little project for graph analytics. And I personally believe that graph analytics will take us to yet another dimension when you can have, 1 trillion edges in a single node. All kinds of exciting things can be done with graph math. So watch this space. So what we do with H2O, we started our journey in the early days. We started to collaborate. Our scientists worked together. We then worked with them on GPU-accelerated driverless AI, which Sri talked about. It's a beautiful product. It helps you automate the process of machine learning and go quickly to the things that really matter. And then we got so interested in them that our venture arm decided to make a small investment in them. And then we created this thing called the GPU Open Analytics Initiative, GOAI, with a company which was then called Continuum, now called Anaconda, really, really important company. MapD, which is now called Omnisci, which is a big database company, and of course H2O and other partners. And today, we're now working with H2O to accelerate the adoption and the performance and the optimization of Rapids. Rapids itself is an open source community. I invite all of you to go to rapids.ai and take a look. All the codes are there, and it's really takes you to this next level. So what does that mean in terms of value to those people who are running all this in IT and have to pay the bills, right? So you, the scientist, you make all this amazing stuff. You say this runs really, really fast, and now you want to go and run it on a data center. So here's something which would be a traditional data science cluster, about 7 or 8 racks of computing, all designed to run your machine learning algorithms. And if you experience the speed-ups of Rapids, then this is what replaces it, right? So okay, so traditional cluster, GPU accelerated cluster. 300 servers, 1 server. 180 kilowatts, 10 kilowatts. $3 million, $400,000. Simple as that. So you create this speed up, you accelerate your algorithms, and the result is you save a ton of money. Okay, so that's the reason you're doing it. Now let's talk about some use cases. So here's a use case that I've been working on for a long, long time. Many years ago, a guy called Matt showed up at one of our GTCs. He was from Walmart. He's one of the people trying to drive change over there. He was looking for new technology to make Walmart better. Here's why. So Walmart has 5,000 stores just in the United States, including, I think, Asda and Flipkart and so on. They have about 12,000 stores worldwide. Each store has at least 100,000 items. Some stores have 1 million items. And each item in each store is a unique SKU. So you can imagine, 5,000 items times 100,000, SKUs per store is 500 million SKUs. And we need to forecast those. If you're in Walmart, you need to forecast the demand for every one of those 500 million items based on the local conditions. For example, there could be a local festival. Halloween is not celebrated everywhere with the same gusto. And so you need to have the right pumpkins and masks and costumes in the right store, for example. So, per store, they have a forecasting model per store, per SKU, and it consumes a lot of computing. It takes quite a lot of time to run, and they need to get that time down to a much more manageable period, and they need to get forecasting done much, much quicker. So they took our Rapids early prototype, they checked it out, they used the XGBoost, gradient boost method, and they got 50 times faster processing. So if you think about it, if you do something 50 times faster, you need 1/50th the amount of computing to get it done in the same amount of time. And so for Walmart, that's a huge amount of saving money. Our other customer is, which is jointly with H2O, is Cisco. And Cisco, whereas in Walmart it's all about consumer demand forecasting, in Cisco it's all about businesses. And businesses, the approach they've taken is to understand customer behavior. So which customer is more likely to buy which stack as a result of which activities. And working with H2O, they tried driverless AI, and they found that things that were taking 1 month to do now get done in 2 days. 1 month, 2 days. Okay, I thought I had a glass of water here. Somebody decided to override it. Okay, so Cisco, 1 month to 2 days. Amazing speed up, better accuracy, better models. I put this one in because there's a lot of talk about medical imaging and AI. And if you just Google medical imaging and AI, you'll see amazing things happening with pathology and ultrasounds and optical diabetic retinopathy, pancreatic cancer diagnosis, and so on. And of course, these medical images take up huge amounts of data. And all of these, there are lots and lots of privacy requirements, anonymizing requirements, and so on. But now here's a more interesting problem, because we are going to start to go towards personalized medicine. And this little company in Oxford called Oxford Nanopore in the Oxford Science Park, just by Littlemore, they have come up with nanopore sequencing. So that little device, you see, it's a little bit smaller than this remote control. This device sequences a whole genome. It's incredible. The whole genome in one little device. And in parallel, the researcher can take with them, this device is called the Mini-Ion, M-I-N, Mini-Ion, and they have a parallel device called a Mini-IT. And the Mini-IT has a GPU-accelerated device, we call it the AGX, the Jetson AGX, and right there in the field, they can go and let's say they're looking for Zika, or let's say they're looking for a crop virus, they can do the sequencing right there in the field, and then with this tiny little computer-powered widget, they can do the whole genome sequencing of a crop virus or a virus that attacks human beings. And now what they've got is a new one, which is called Prometheon. And the Prometheon is for much bigger genomes, like the human genome. A virus is about 400K, 400,000 base pairs. Human genome is 3G, 3 billion base pairs. And so you need something more powerful. And what they've done is they've taken that same exact input device and connected it with a much bigger computer with 4 of our big Volta processors. And that can do a human genome or a wheat genome sequencing in about $800 or so. And of course, once you start to do that, then you can do all kinds of exciting analytics. It used to be that you use these older style traditional algorithms like Smith-Waterman and BLAST and Bowtie for genomic analysis. And what Oxford Nanopore has shown is you can do it a different way. You take the nanopore that comes out, molecule by molecule, all the ACGTs, and instead of looking at it in a traditional way, you convert it into a recurrent neural network with LSTM as a time series recurrent neural network. And using that, you can get for whole genome sequencing close to 95% accuracy as compared to about 80% accuracy with traditional ways such as 23andMe and so on. So this is a new way of doing things, and it's going to change the dynamics of healthcare as we move towards more personalized medicine or more interesting food and issues that we have around food. So Sri already talked about PayPal. We think they're a really, really cool customer, jointly with H2O AI, hundreds of millions of users, all kinds of interesting fraud detection patterns. And of course, PayPal only do a few hundreds of transactions, maybe 1,000 transactions per second. But just think about VisaNet and MasterCard and Capital One and the size of the data sets they have there. It's very, very compelling. In the case of PayPal, you're looking at increasing accuracy from less than 90% to above 95%, and speeding up the computing by a factor of 6x. This is an interesting one. This is a DFKI, the Dutch Research Institute for Artificial Intelligence, the German Research Institute for Artificial Intelligence. And you can see here, they were demonstrating this in Munich. They're taking data feeds from Twitter, from social media, from obviously their government database, the German Weather Service. And so you think about like a problem. For example, in June, there were lots and lots of floods across all of Germany. All the levels were rising. Where do we put, as a German government, where do we send the relief agencies to, boats, the rescue, the emergency services? How do we mobilize as a country in the face of this potential natural disaster? Or how do we prevent something like, the Berlin truck attack? So these are the kind of problems that they're working on using neural networks, deep learning, and now machine learning. And then, lastly, I love this one. This is Neuro, a little company made by two Google engineers who used to be working in Waymo, and they thought that their delivery robot was better. Every single retailing company is looking at solving the last mile problem, whether it's JD.com or Amazon.com, or in this case, Kroger's. Kroger's is the second largest retailer, third largest retailer in the US. And they are trialing out now in Scottsdale, Arizona, this Neuro software for last mile delivery. So this car that you see in front of you, it comes and it shows up in front of your door or your mailbox. It sits there till you bring your app, and the app unlocks it just like it unlocks your bicycle if you were using one of the bike sharing companies. And then you open it, pick up your deliveries, take it home, the app closes it. That's kind of a pretty cool example of what you can do with deep learning and machine learning. By the way, the delivery logistics problem is a huge one because it's two-sided. And those of you working on this know that. So here's my conclusion. You need mathematics, simulation, high-performance computing. Navier-Stokes doesn't go away. Monte Carlo, Markov chains, many of you using in financial services, don't go away. We need that high-performance computing for simulating the math and generating the data so we can compare it against the actual data set. At the same time, we need to look at these huge data sets that we have and start to make sense of them using deep learning and machine learning. And I think Rapids is a significant contribution on that journey. And then, of course, once we've done all the simulation, whether using equations or data sets, we need to visualize it. And what GPU computing is offering you is one architecture, the same architecture for all of these modalities. And you can run it on the device, inside the surgical instrument, in the car, in the edge, on premise, and in the cloud on all the cloud providers. So how do you get started? And we have sort of three things. One is the GPU Technology Conference, rather like H2O's conference that you had here. Or we can do a Deep Learning Institute. You can just log in, Deep Learning Institute, and it'll spin up an instance for you, or you can come on site and you can, we call it the Deep Learning Institute, but it does normal computer vision and CUDA and now Rapids. Or you can just go to the cloud, NGC and download a container and start loading it up. So if you go to rapids.ai right now, you will see two things. One is the data frame with Anaconda, and then you'll also see an NGC container with the CUML. And that includes the Fannie Mae dataset, so you can download it. Hopefully you've got 400 gigabytes of space. Maybe you can do a subset of it. And actually get started with analyzing mortgage risk using GPU-accelerated machine learning. And you know, the thing about this last night I was with one of our customers, and you know, he's experienced this speed up. And you know, he said it's kind of like, if you've never been in a car and pressed the accelerator to go from 0 to 100 in 5 seconds, you have no idea what speed up means, okay? If you want to experience that speed up, you've got to run it yourself, and you will feel it in your gut. It'll get your adrenaline going, and then you can start to change your company and take it towards making it a computing company. Thank you very much for your time. Thank you for listening. And, thanks for seeing the team. Thank you.